Hey gang, this video is going to start our next unit of study, which is over linear functions. So in this first lesson, I'm just going to review a lot of terminology with you dealing with relations and functions from Algebra 1. So we're going to start out with some terminology describing relations. So a relation, we learned last year, is just a set of ordered pairs, and relations can be shown in multiple ways. We can show relations using a table, a mapping diagram, and more often than not, you'll see them represented as graphs or equations. Those are the two most common forms that we use to represent relations. The set of x values in a relation is called the domain, and the set of y values is called the range. If we have a relation with distinct points on a graph that would look like a scatter plot where the points are not connected, we call that a discrete relation. And if it's a relation on a graph with connected lines or curves, that is called continuous. And then moving on from relations, we have specific types of relations that we refer to as functions. So a function is a relation in which each element of the domain is paired with exactly one element of the range. And so what that might look like would be this. If I had the set of ordered pairs 0, 1, negative 5, 2, negative 6, negative 2, and 5, 7. Okay, every domain value, 0, negative 5, 6, 5, is paired with only one range value, 1, 2, negative 2, 7. So this would be an example of a function. A non-function would be a relation that looks like this. Let's say I had negative 7, 2, 6, negative 1, 6, 2, and negative 3, 9. So this would be a non-function because this domain value of 6 pairs with both negative 1 and positive 2. So the simple way to remember this is the x values cannot repeat. If your x values repeat, then your relation is not a function. If the x values don't repeat, then it is a function. The way to tell whether a relation is a function when in graph form is to use what's called the vertical line test. And so that's where we attempt to intersect our graph in more than one point with a vertical line. So for this graph here, I have this diagonal line. You can see that no matter which vertical line I draw on this graph, every single vertical line only intersects this graph in one point. So this graph would be a function because it passes the vertical line test. Something like a circle, though, I can draw a vertical line that will intersect the graph in two different places. Okay, this vertical line, for instance, intersects our circle here and here. So anytime you can draw a vertical line that does this, the graph is not a function. If you can't do that, then it is a function. So here in examples 1 through 8, I've given you some different representations of relations. And so in these, we're going to first of all find the domain and range of each, and secondly, tell whether or not each relation is a function. So for the domain and range, if they're discrete relations, meaning they're just regular sets of ordered pairs, we just list those values in order from least to greatest in braces. So number 1, my domain values would be the x-coordinates, and those would be negative 3, positive 5, and positive 8. Those are my 3 x-coordinates in this relation. It's not necessary to repeat the 5 when you're listing the domain. The range values would be the y-coordinates, and that would be negative 6, 0, 2, and 4. This relation is not a function because you can see we have a repeating x value of 5 here and 5 here, so this is not a function. Number 2, this is in table form. The domain values are simply all the x values, so that would be negative 4, 0, 2, and 7. The range values are the y values, negative 8, negative 1, and 3. This relation is a function because if you look at your, again, domain column or your x column, we have no repeating x values. So this is a yes function. Number 3, this is what a mapping looks like. Our domain values, again, are in the x circle, so that's -4, -2, and 5. The range values are 0, 3, 7, and 9. This relation is not a function. You can see we have 2 arrows coming from this domain value of 5. 5 is mapping to 7 as well as 9, and so that means this is not a function. That's just like having repeating 5s up here in example 1. For example 4, our domain values for this are 2, 8, 13, and 17. The range values -4, 0, and 7. This mapping does represent a function because each domain value only has 1 arrow extending from it, meaning it only has 1 range value assigned to it. So this is a function. Okay, now I've given you a couple of examples of graphs of relations. So when I give you this is, by the way, and again, example of a discrete graph because we have our points that are not connected. It's just 1, 2, 3, 4, 5 random points on the coordinate plane. The domain values you're going to get by looking at the x-coordinates of each of these points. So here, these points both have an x-coordinate of -3. This point here has an x-coordinate of 0, +2 for this point, and +4 for this point. So our domain values -3, 0, 2, and 4. The range values, you just look at the y-coordinates. So starting at the bottom, we have -5 for this point, -2 for the y-coordinate here, -1, +1, and +4. Because this is a graph, I can use the vertical line test to tell whether or not this is a function. And if I draw a vertical line, you'll see here on x is -3, I hit both of these points at the same time, so this is not a function. This fails the vertical line test. For number 6, this is an example of a continuous graph because all of our points are connected. So anytime we have continuous graphs, we describe the domain and range using inequalities or all real symbols. So the domain of this graph, you have to think how far left and right can you go on the graph? Well, our graph only goes to a certain point on the x-axis. It stops right here at an x value of -4, and then it extends right in both directions. So we could say that the domain of this graph is all x values that are greater than or equal to -4. The range of this graph, well, because it goes forever in a negative direction, okay, in terms of the y values this way, and forever in a positive direction this way, there's no limit on the minimum or maximum y value. We would say the range is all reals for this graph. Is this graph a function? The answer is no, because again, I can use my vertical line test and draw a vertical line here that intersects the graph in 2 spots. For number 7 and 8, I've given you equations and asked you to determine the domain, the range, and the function. For these, you actually want to get your graphing calculator out and graph these on your calculator if I give you the equation. So for number 7, I've given you the equation y equals -x squared plus 3. So we'll go to our graphing calculator and we'll graph -x squared plus 3. Hopefully you remember from last year, this is a quadratic, so this gives us a parabola. All I'm concerned with, what is the domain, what is the range? Well, the domain values, if you look at the graph, it goes forever to the left and forever to the right. So in this case, the domain would be all reals. The range, however, is restricted. this graph has a maximum y value of positive 3. Okay, here we have a maximum point of 0, 3. So the range of this graph would be all the y values that are less than or equal to positive 3. Is this graph a function? Well, if you look back at the graph, you can see hopefully that it will pass the vertical line test. All parabolas that are opening upwards or downwards do that, so this is a function. Okay, number 8, y equals negative 5x minus 1. That's an example of a linear function, so we'll graph that as well on our calculator. Just so we can see what the domain and the range would be by looking at the graph. All diagonal lines have a domain and a range of all reals. Okay, they go forever to the left and right in both directions and up and down. So the domain and range of this graph will be all reals. And to answer whether or not it's a function, all diagonal lines are functions. So that's a yes. They always pass the vertical line test. Okay, moving on to function notation. Function notation is simply a different way to write equations. Equations that represent functions are often written using this function notation form, and all it involves is replacing that variable y with the symbol f of x. So again, if you see equations in this format, it means the same thing as y equals. It's just a way of saying that this is a function. And we use function notation a lot when we're evaluating functions. So if I said, okay, f of x equals 2x plus 7, find f of negative 3, that simply means I want you to replace the x value with negative 3. So to find f of negative 3, we would take 2 times negative 3 and add 7. And f of negative 3 would end up being positive 1. So in examples 9 through 12 here, I've given you a couple of different functions, an f of x equals negative 5x minus 14 and a g of x equals negative x squared plus 9x minus 1, and asked you to find either f of or g of an input value. So number 9, f of 3/10 means we're going to take the f of x function and we're going to substitute 3/10 in for x. So we'll take negative 5 times 3/10 minus 14. Negative 5 times 3/10 gives us negative 3/2. And negative 3/2 minus 14 becomes negative 31/2. Number 10, g of negative 7. I need to take my g of x function and substitute in negative 7. So we have a negative sign in front of the x squared. Then we'll plug in our negative 7 for x, squaring it, plus 9 times negative 7 minus 1. Negative 7 squared is positive 49, but the negative in front of the x squared changes this back to a negative. So we have negative 49 minus 63 minus 1. And we get an answer of negative 113. Number 11, f of 1 minus f of negative 4. So we're going to do this in a couple of different steps. We'll start by calculating f of 1. So f of 1 would be negative 5 times 1 minus 14. And that gives us negative 19. And then we'll calculate f of negative 4. F of negative 4 is negative 5 times negative 4 minus 14. That's going to be positive 20 minus 14, which is positive 6. And this asks us to take the value of f of 1, which is negative 19, and to subtract f of negative 4, which we know is 6. So we're going to do negative 19, subtract 6, and we'll get an answer of negative 25. Number 12, this is telling us to take 2 times g of 12. So we're going to start by finding what g of 12 is. So g of 12 is going to be negative 12 in parentheses squared plus 9 times 12 minus 1. 12 squared is 144. The negative sign out front here makes this a negative 144 plus 108 minus 1. And we end up getting negative 37 for g of 12. We then are going to take our 2 times g of 12, so this will be 2 times negative 37. And our final answer will be negative 74. Okay, moving on to 13, 14, 15, and 16. Same concept, function notation. This time I've changed the functions for you though. I'm telling you p of x is 1/2 minus 4/3 x, and q of x is the absolute value of 3x minus x cubed. So just getting a little bit more challenging here. Q of negative 2 would look like this. So I'll substitute a negative 2 in for x into those absolute value symbols. And again, be very careful with your use of parentheses here. So this is how that substitution should look, plugging the negative 2 in here and here. From there, it's just your order of operations. So 3 times negative 2 we know is negative 6. Negative 2 cubed is negative 8. But don't forget we also have this minus sign here in front of that. So this is really a minus negative 8. We know that minus negatives can be rewritten as positives, so this is really negative 6 plus 8 inside the absolute value bars. From there, you simply do negative 6 plus 8, which is 2, and the absolute value of 2 we know is 2. 14, p of 18. So this will be 1/2 minus 4/3 times 18. 4/3 times 18 is 24, so this will be 1/2 minus 24. And this becomes negative 47/2. For 15, this is asking us to take 7 minus q of 4.5. So we're going to start by finding what q of 4.5 is. So q of 4.5 is going to be the absolute value of 3 times 4.5 minus 4.5 cubed. This is where calculators come in handy. 3 times 4.5 is 13.5. 4.5 cubed is actually 91.125, so this is minus 91.125. Inside the absolute values, we end up getting a negative 77.625, and so because it's absolute value, that would become a positive 77.625. So this value goes in for q of 4.5. Again, these are equivalent. So for our final answer, we need to take the 7 in the original problem and take 7 minus 77.625. And when I do that, I get an answer of negative 70.625. Okay, number 16, 3 times p of negative 1 plus 5. I want you to pause the video and try this one on your own. Once you think you have an answer, click play to check. Okay, so for 16, we need to start by finding p of negative 1. If you do that correctly, you should get p of negative 1 equals 11/6. And then we plug 11/6 in for the p of negative 1. So we're taking 3 times 11/6 plus 5. You end up getting a final answer of 21/2 for number 16. Okay, there are more examples on this on these note sheets, but we're going to actually take a look at those in class. So you can stop the video right here. We'll finish this up in class the next time I see you. Have a nice day. You're all wonderful people. Take care.